Welcome back, students. In this video segment, we will cover the first half of section 7.7, Approximate Integration. Okay, so I decided to cut section 7.7 into two parts and do two separate videos. It's a long section. In the first part, we're going to look at formulas for estimating the values of definite integrals. So I'd like to put this section in kind of a framework in terms of where it falls into place in your math learning for science courses. The first part of this chapter, in fact, the sections 7.1 up to now, involve finding antiderivatives of functions, a very important list of formulas for finding antiderivatives. Now, I mentioned earlier that the idea of finding antiderivatives is difficult at best in reality. At very, very best, it's in fact, at very, very best in real everyday usage, it's impossible or very, very difficult to find an actual antiderivative of a function. So how is integration actually done in practice? Most of the time, almost 100% of the time, integrals are not found by using the fundamental theorem of calculus, that is finding antiderivatives, but by estimating integrals. So let me give you a couple of scenarios where we would need to do something other than finding an antiderivative. There are two situations I can think of where we can't find the actual value, the exact value of a definite integral. So the first case would be we can't use the fundamental theorem. So let's be more specific about this. So we'll look at cases where it's impossible to find the exact value of a definite integral. The first case is we can't use the fundamental theorem of calculus. The fundamental theorem, I'll abbreviate, of calculus. And where that might happen is where we can't possibly find an antiderivative. It is impossible, let's say, for example, to find the integral of e to the minus x squared to evaluate the definite integral, say, between 0 and 1 of e to the negative x squared dx. This function is a very famous function. It's very closely related to what's called in statistics the normal probability distribution, e to the negative x squared. And evaluating definite integrals of e to the minus x squared is very important. It amounts to figuring out the probability of certain events occurring. And this is hugely important in the sciences. We can't possibly find an antiderivative, at least with simple elementary functions, of e to the negative x squared. Now later on you're going to see that we can actually evaluate the indefinite integral of e to the negative x squared, but it's going to involve an infinite sum of simple functions. Okay, so in this case, in the first case, we can't use what we've learned in Calc 1 and Calc 2 to simply find the antiderivative for e to the negative x squared. The second case that is pretty common is that when evaluating, let's say, the integral from a to b of f of x dx, f of x is not given explicitly. I'll explain. In the sciences, we gather data. We gather data at regular, let's say, time intervals. So you may say you may be observing the velocity of an object moving across the sky, or in a velocity of a particle moving in a physics lab. And you're able to, let's say, measure the velocity every 100th of a second. Every 100th of a second. So you measure the velocity at 0, t equals 0, time equals 0, then at time equals 0.01, then time equals 0.02, time equals 0.03, etc., etc., etc. This is very common, this type of scenario. But we still need to figure out the area underneath the velocity curve. We still would like to be able to predict the displacement of the object during a certain time interval, say from 0 to 1 second. And if you recall, the area underneath the velocity curve gives us the displacement. This is displacement of the particle. Okay, so what I'm heading toward here is the idea, and this is just a very brief example here. The idea here that my function is not given to me explicitly. So here's what I was talking about. Suppose we graph along the y-axis velocity and along the x-axis time. And we observe the velocity of the object at time equals 0.01, then time equals 0.02, then time equals 0.03, etc., etc., etc. And we get a bunch of dots. We get a bunch of data points. Okay, and this goes on and on and on. I'm still interested in whether I have a function explicitly or not. I'm still interested in the area underneath the velocity curve. So suppose that there is some sort of theoretical velocity curve that would pass through these series of points. And I'm interested in the velocity, or in the displacement of the particle in the first, let's say, in the first second of its motion. Okay, so the first second of its motion would be from t equals 0 to t equals 1. Well, the displacement is equal to the integral from 0 to 1 of the velocity function. Well, why can't we use the fundamental theorem? Because we don't have a velocity function. All we have is a series of dots. So the only way to estimate the area underneath this theoretical velocity curve to get the displacement would be to estimate the value of the integral. Okay, which leads us to our lecture for this segment and the following segment. How do I do that? Well, I'm going to use my drawing here. Actually, I didn't plan on it, but I'm going to use my drawing here to illustrate how that would be done. If I want the area underneath this curve, what I could do is use my Calc 1 and use the series of dots as right-hand endpoints of rectangles, and then estimate my integral by adding up the areas underneath these estimating rectangles. This is what we did in Calc 1 before we fired off into the fundamental theorem, and then we never had to do this again. If you recall, we defined the definite integral by estimating the we defined the definite integral by saying that the definition of the definite integral gives us area, and we can then use an infinite number of rectangles under the curve via what we call Riemann sums to define that integral. So that didn't come out very well. In fact, we're gonna be looking at the definition of the definite integral again. So if you're any bit confused, this was sort of an impromptu example that I don't think came off very well. So here goes. This section involves going back to the definition of the definite integral. the definition of the definite integral has nothing to do with antiderivatives. Antiderivatives came around with the fundamental theorem of calculus. Part 2 of the fundamental theorem of calculus said that we can evaluate definite integrals by first finding an antiderivative of the function in question, and then taking the difference between the values of that definite integral at the endpoints of the interval a and b for our integral. So let's we have to look back at the definition of the definite integral. So we're going back to Calc 1. The definition of the integral from a to b of f of x dx. So let's do that. Let's assume that we have a continuous function y equals f of x, and that continuous function is defined between 2 points along the x-axis, a and b. Okay, so what we did to define the definite integral in Calc 1 is that we imagine the interval from a to b divided up into n subintervals of equal length delta x. So we imagine taking the interval from a to b and chopping it up into n subintervals of equal length delta x. So here's the first subintervals from a to a plus delta x. Here's the second subinterval. Here's the third subinterval. Somewhere along the line in between a and b, we have a typical subinterval, number I subinterval. And then we go to the end of the interval from a to b to look at number n subinterval. And each of these subintervals is supposed to have length delta x. So the length of the first subinterval is delta x, the length of the second interval is delta x, etc., 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 etc. Okay, so once we've divided up the interval from a to b into subintervals of equal length delta x, we should identify a couple of things. We should identify what delta x equals, and we should identify those points between a and b. So delta x is equal to the length of the whole interval between a and b, which is b minus a. Remember, the length of an interval, a closed interval from a to b, is the right-hand endpoint minus the left-hand endpoint. Okay, so we're going to divide that interval up. So it's the length of the whole interval, b minus a, divided by the number of subintervals. So there's the length of each of the delta x's. Okay, we should also, again, identify those points between a and b. So I'm going to call the actual point a x sub 0. And then I'll call the first, the endpoint of the first subinterval x sub 1, and x sub 2, then x sub 3. In the third subinterval, in the number I subinterval, I'm going to call that x sub I. And I'm going to keep going until I get to the last subinterval, which will involve the b as being x sub n. And then just before that is x sub n minus 1. Okay. Okay. The next thing we do is within each of the subintervals, this is where it gets a little tricky, real kind of abstract, as if it's not abstract enough. The next thing we do is within each of the subintervals, we randomly select one point. Okay. And the point that we select in the first subinterval is a random selection of a point between a and x1, and the selection between x1 and x2 of a point has no bearing on what we selected in the interval just before it. We're selecting n random points. So we're going to identify those, and I'm going to do that in green here. In the first subinterval, I'm going to pick a point at random. And I'm going to identify it as x sub 1 star. In the second subinterval, I'm going to do the same thing. In the second subinterval, though, that point that I'm identifying has nothing to do with the point that I selected in the first subinterval. So I'm going to call that x sub 2 star. In the third subinterval, maybe I'll take one around the midpoint. I'll call that x sub 3 star. And we keep doing that in each of the subintervals. In the typical a number I subinterval, I'll choose an x sub I right about there. We keep doing that until we get to the number n subinterval. I'll pick it right about, let's say, here. In the number n subinterval, I randomly select a point. The point can be the left-hand endpoint, the right-hand endpoint, the midpoint. It makes no difference. The definition of the definite integral does not depend on the point that I select in each of the subintervals. Now this is where in Calc 1 we started to use the interpretation of the definite integral as area. Now the definite integral in general has nothing to do with area. It's a very abstract quantity that's some sort of, and you'll see this happening very soon, is some sort of limit. But we can interpret the definite integral as giving us area as long as the function lies above the x-axis. So as long as we're looking at a non-negative function, then we can interpret the definite integral as area. And this was very helpful in Calc 1. So let's imagine then we're thinking about finding the area underneath this curve and associating it with the definite integral. So what we would do is in the first subinterval, we would go to that x sub 1 star, and from there we would go up to the curve. We go up to the curve and use the y value there as the height of a rectangle that's being used to estimate the area underneath that curve within the first subinterval. Okay, and what would the actual area of that rectangle be? Well, the area of a rectangle is very, very simple. It's the length times the width of the rectangle. Well, the length of the rectangle is the y value at x sub 1 star. So at x sub 1 star, you're looking at f of x sub 1 star, that's the y value there, times the width of the rectangle. Well, the width of the rectangle is the delta x. And that gives me the area of that first red rectangle. And to that we would add the area of the second rectangle, which we would get by going to the second starred x value, x sub 2 star, and go up to the curve at that point. That gives us f of x sub 2 star. That will give me the height of my second approximating rectangle. So algebraically then, I'm going to add to the area of the first approximating rectangle the area of the second one. The height is the length rather, is f of x sub 2 star, or height, times the width delta x. And we continue this, and I'll do one more here before we get to the typical one in the middle somewhere. At x sub 3, we go up to the curve. That height is f of x sub 3 star times the width delta x. So f of x sub 3 star times delta x. That's the area of the third approximating rectangle. A typical approximating rectangle somewhere between the first and the number n rectangle would be at a typical f of x sub I star. So I go up to the curve at x sub I star. That forms a rectangle of height f of x sub I star. And I go up to the curve. So to the original expression then, algebraically, I'm adding up all the areas of the approximating rectangles. And I do this, I keep going until I hit the last approximating rectangle, the number n approximating rectangle. At x sub n star, I go up to the curve. I use that y value there as the height of the approximating rectangle. The width looks longer. It should still be delta x, but it looks a little longer in my drawing. Discovered I'm not an artist. My drawings are really, really, really poor. Okay, so algebraically we add that last area. So f of x sub n star, so I star, forgot an I on I star, delta x. And then we used sigma notation to collapse this sum to make it a little easier on the i's. Capital Greek letter sigma for sum, so you could read this as the sum of f of x sub I star. It's a typical area of a typical rectangle, as I ranges from the first rectangle to the number n rectangle. And this gives me what I'll call the sum s sub n. It's s sub n, sum of the first the areas of the first n rectangles. This sum has a very, very important name. This is called a Riemann sum. Riemann sum. Again, this is just a rather lengthy reminder of what we did in Calc 1. We need this reminder. Now, that gives us the approximate area underneath the curve. But those approximating rectangles don't give us the exact area underneath the curve when we add their areas up. However, when we stuff in more and more and more rectangles, that is, we let n get bigger and bigger and bigger, the amount that we're going to be off by using approximating rectangles gets smaller and smaller and smaller. So our error, the error involved in approximating our area by using Riemann sums, shrinks smaller and smaller and smaller as n approaches infinity, as the number of rectangles becomes infinite. And that's how we get the definition of the definite integral. When we take the limit, I want to switch to black pen here. When we take the limit as n approaches infinity, as a number of rectangles approaches infinity, then we get the limit as n approaches infinity of the Riemann sums. I goes from 1 to n, f of x sub I star delta x. And this is a definition of the definite integral. This is how the definite integral from a to b of f of x dx is defined. And I think a lot of students would not state this as the definition if they were asked. I think that a lot of students, after taking Calc 1, and if they were asked to state the definition of the definite integral, they would state the fundamental theorem of calculus. No, this is the definite integral. This is the definition. Okay, so what does this have to do with us? Well, not only does it have to do with us, it has to do with you as a science major. If you plan to follow through with, and I hope that you do, with your major and get a science degree, you're going to be integrating. And how you're going to be integrating is this. So the definite integral from a to b of f of x dx is then approximately equal to the sum, I goes from 1 to n, of f of x sub I star delta x. This is how it's done in practice, in reality. This is how integration is done in reality. We take off the limit because we can't possibly evaluate or observe an infinite number of observations. Remember, we were talking about that, observing the particle moving. We can observe the velocity of a particle at a whole lot of positions. We can observe that. We can use a machine or a device to observe the velocity of a particle at hundreds of thousands, if not millions of locations, but it's still finite. The data are still only given as a finite data set. Okay, so this is how in real life integrals are approximated. So, or evaluated by approximation. Now notice that we are approximating an integral. So every time we estimate something or approximate something, we introduce something to the problem that we didn't have in Calc 1 when we were finding exact values. What do we introduce? What is it called? When we estimate something, what do we automatically get that we really don't want? But what do we automatically introduce to the problem? It's called error. And error is extremely difficult to compute. There is a whole branch of mathematics that's centered around approximating quantities in mathematics and then keeping track of the error involved in approximation. So what makes error so absolutely difficult to get a hold of? Well, error, which we can say is, or give a variable e for, capital E for error. Error equals the true value of your quantity minus the estimate, approximation. So the true value is the actual value of the integral from a to b of f of x dx minus the estimate gives us our error. So why is it such a difficult quantity? Because in order to figure out the error, we would have to know the true value of the integral. If we could figure out the true value for the integral, then we would have no need for the error. The problem is we don't have access to the true value of the integral. How do we estimate error? We estimate error through some very complicated formulas that have been discovered by mathematicians and scientists. And that's going to be the hardest part for us of this section 7.7. In fact, it's what we're going to devote part 2 to this section on in the next video. We will dedicate that entire section to estimating error. Okay, so now what we need to do to finish up this section, and we got quite a ways to go in this video segment. What we need to do is develop and look at different formulas for estimating integrals. And then in part 2, we'll look at getting a handle on error. Now the nice thing, if we can say that about this first video segment, is that ultimately the formulas are just a list of formulas. They look kind of complicated at first, but they're just formulas, a list of formulas. This is the easy part. Part 2, the getting a handle on the error, is the more complicated part. So let's dig into looking at formulas, popular formulas for approximating integrals. The first 2 formulas I'm going to bring up are not going to be ones that we use very often. In fact, very little, if any, effort is going to be expended in using these first 2 formulas. Mostly these first 2 formulas are to remind us of what we did in Calc 1 and to help and to use that reminder to sort of segue into more popular methods. And I'll explain why the first 2 are not real popular. Basically, I'll let the cat out of the bag. The first 2 are not popular because they're grossly inaccurate. Okay, so what am I talking about? Let's go back to the definition of the definite integral. So what I did is I drew a real quick drawing of our curve again. And what I'd like to do is to put in those points, the x0 up to xn. They're going to follow us through all of these estimation methods, x0, x1, x2, not the start values, just the endpoints of the subintervals, x sub I minus 1, x sub I, x sub n minus 1, and x sub n. Okay, So the first method that I'd like to bring up is one that's very commonly brought up in Calc 1, and that's called a right endpoint approximation, or right endpoint approximation. So what we do is we imagine that we select those starred x values as the right endpoint of each of the subintervals. So in the first subinterval, as the x1 star, I'm actually going to choose x1. On the left of the first subinterval is the point A, or x sub 0, and the right is x1. So I'm going to choose x1. Then we go up to the curve. So geometrically we go up to the curve. And then we're using that right-hand endpoint to form a rectangle. In the second subinterval, we do the same thing. We go to the right, between x1 and x2. On the right is x2. We go up to the curve. We form a rectangle using the y value there at x2 as the height. And we keep doing this at x sub 3, up to the curve, form a rectangle. Somewhere in the middle at x sub I, go up to the curve, form a rectangle. Okay, and we keep going to the end. So at x equals b, that's on the right in the last subinterval, we go up to the curve, form a rectangle. Okay, so what we get is, what we still have is delta x equals b minus a over n. And what we get is something called a right endpoint approximation. By choosing the right-hand endpoint of each of the subintervals, we get what's called a right endpoint approximation. So our integral of f of x with respect to x from a to b then is then approximately, and I'm going to use for the symbol for the right endpoint approximation r, and I'm going to give it a subscript of n indicating the number of subintervals we're choosing. And that is, well, rather than bringing up the formal Riemann sum, let's just write it out. The area then would be the value of the function, at x sub 1, that's the height, times delta x, plus the value of the function at x sub 2 for the second rectangle, times delta x, plus all the way up to the value of the function at x sub n, another name for x sub n is b, times the width of the rectangle. And that's our first formula. That's the formula for the right endpoint approximation using n subintervals. Very commonly, though, it's written in a kind of a shorter notation, not with the sigma notation. We can write our sums out. We'll be using sigma notation a lot in the course coming up. But for right now, we can just write the sums out. Notice I can factor a delta x out and then write this as the delta x times f of x sub 1 plus f of x sub 2 plus all the way up to f of x sub n. And that's our first formula. And this formula is something you used in Calc 1. Very, very high probability that your instructor used right endpoint approximations. At that point in Calc 1, though, you let n approach infinity, and that's one of a couple of nightmares for students in first semester calculus. Riemann sums, related rates, and optimization problems seem to be the three big things in Calc 1, but I'm really moving off into a tangent here. Okay, so there's our first formula. The second formula, which is also one that we're not going to use, and I kind of indicated why, but I want to come back to that in a minute, is called a left endpoint approximation. Left endpoint approximation. Endpoint approximation. approximation. The left-hand point approximation is abbreviated as L sub n, so the integral is still the integral from a to b of f of x dx, and that is approximately L sub n. And L sub n, instead of taking the right endpoint of each of the subintervals, we take the left endpoint of each of the subintervals. Okay, so maybe to make it really stand out conceptually, I'll do this in green in the same drawing. So now imagine going back to our drawing that's filled up with a bunch of right endpoint approximating rectangles. Then now we do the same thing with left endpoints. In the first subinterval, the left endpoint is x sub 0, or a. If we go up to the curve at that point, here will be in green the y value at that point. We're going to use that as the height of the first rectangle. Come back down. So that first green rectangle is what we get by using a left endpoint approximation. And that would give us the area of that first green rectangle would be f of x sub 0 delta x. Okay, let's move this along a little bit. So in the second subinterval, we would pick x sub 1 for the left-hand endpoint. X sub 2 was on the right, x sub 1. We go up to the curve at that point, form a rectangle, and there's the area of the second approximating rectangle using left endpoint approximations. What is it equal to algebraically? F of x sub 1 delta x. And we continue this until we get to the very end. At the very end, we would look at f of x sub n minus 1, of n meaning the last subinterval, f of x sub n minus 1 at the last subinterval. Go up to the curve at that point on the left, and that green rectangle is our number n approximating rectangle using left endpoint approximation. F of x sub n minus 1 delta x. X sub n minus 1 is on the left of that in that nth subinterval. Okay, so just as I did before, I'm going to factor out a delta x, and our formula then looks like delta x times f of x sub 0 plus f of x sub 1 plus dot 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 all the way up to not f of x sub n, but f of x sub n minus 1. Okay, and the formulas look very similar for r sub n, r sub n, and l sub n. They look very, very similar. R sub n starts it with x sub 1 and goes all the way up to x sub n. And L sub n starts at x sub 0 all the way up to x sub n minus 1. Okay. Now what I want to do, before we dig into the approximating methods that are actually used, is I want to bring up an integral that we're going to be estimating over and over and over again. The same integral we're going to estimate over and over again using different methods with different accuracies. We're going to use a right endpoint approximation to estimate this integral. So I want you with me to consider the integral from 1 to 2 of 1 over x with respect to x. This integral is going to follow us through the remainder of this section and the next section. Okay, why did I choose this one? Because we have the ability to find the exact value of this integral right away. So we can look at its value right away. What is the value of this integral? I'll give you a couple of seconds to think about it. What's the value of this integral? It is the natural log of 2. This is the natural log of 2. So we have the value of this integral without having to look at an estimate. Use our calculator, which ironically uses an estimate. Okay, so our first example of applying an approximation method is to estimate this integral. Okay, so use a right endpoint approximation. Right endpoint approximation to estimate the integral from 1 to 2 of 1 over x dx. In other words, I want r sub 5. Okay, so that is find r sub 5. And I realized as soon as I said it means find r sub 5, is that I never stated in the problem what n should be. So that was my blunder there. I'll fix that. So use a right-hand endpoint approximation to estimate the integral with n equals 5. And that means find r sub 5. Okay. Now to do these problems, I think it would be a good idea for you to consider not a graph of the function, that's not really necessary here, but just a graph of the part of the x-axis that we're considering. So it's real useful to, in setting up these problems, draw a picture of the x-axis between the 2 points we're integrating. So we're integrating between 1 and 2. So here's x equals 1. Our integral approximation is going to involve the width of the subintervals. The width of the subintervals is, remember, it's b minus a over the number of subintervals, or 2, that's the interval, that's the number on the right, minus 1, number on the left of the interval, the big interval, over the number of subintervals, 5. That's 1 over 5, and that's 0.2. So the first right-hand endpoint then will be, let me put it right here, a delta x away, 1 delta x, or 0.2 away from 1. Well, what's 0.2 away from 1? It's 1.2. So the next endpoint, the next right-hand endpoint in the second subinterval then is 1 delta x away from 1.2. Well, 1.2 plus 0.2 would give us 1.4. So the delta x's are the distances between these points. So between 1 and 1.2 is 0.2. Between 1.2 and 1.4 is 0.2. What's the next one then? It's 1.6. Then 1.8. Then 2. Okay, and each of the subintervals has length delta x. How many subintervals are there? Count them up. There are 5. Okay. So now we set up our approximation. So the integral from, let me separate this off here. The integral from 1 to 2 of 1 over x dx then is approximately equal to r sub 5. And remember our formula for the r sub n is delta x times f of x sub 1 plus f of x sub 2, etc., etc., etc. So it's delta x and n equals 5, so times f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus f of x sub 4. This gets real tedious when n equals like 1,000,000. Not for you guys. I promise I won't let n equal 1,000,000 on your next test. Promise, I promise, I promise. Okay, so that's what the formula looks like written out. So let's put some numbers in here. Delta x is 0.2 times f of x1. Well, x1 is 1.2. 1.2. x2 is 1.4. 1.6 for x3. 1.8, so f of 1.8 plus f of 2. This line is what you show on your exam. and I think it would be a good idea on your homework also. This right here, I'm going to write it in red actually. This right here, this line right there, show this on exam / homework. Okay. So when my grader looks at your work, she's going to look for this line, 0.2 times f of 1.2, etc., 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 all the way up to f of 2 or whatever, okay? Then, what else do you show? Nothing. There's nothing else for you to show. Well, I guess we should show the answer, huh? Well, there is one more thing to show. That's the answer. That's the only other thing you show. Now, what I'd like to do is take a second to show you how to do this efficiently in your calculator if you have a Texas Instruments graphing calculator. If you have a different calculator, I'm not going to be able to help you with that in this video segment. But they're all the calculators are fairly consistent with this kind of keystrokes, as far as I know. Okay. So what you do in your calculator, I guess I should do this in a different color. So calculator. First, enter the function. Enter the function f of x equals log, or not log of x, f of x equals 1 over x as y sub 1. Y sub 1. Okay, which involves, if you haven't entered, you must have entered functions in your graphing calculator, pushing the y equals button in the other upper left and then just entering 1 over x. Okay. So what this means in our calculator, and you don't have to write what I'm writing in green here on your exams, but this is just for us. This means 0.2 times y sub 1 of 1.2 plus y sub 1 of 1.4 plus y sub 1 of 1.6, etc., etc. Well, there's only two more, so I'll write them in. Y sub 1 of 1.8 and y sub 1 at 2. Okay. So what you enter in your calculator to compute these y values is one of two things, depending on how old your TI-84 calculators. The earlier versions of the TI-84 calculators don't have a shortcut menu for the y's. So I'll show you right now. So let's see, I need a couple more colors here. So in blue, this is what you would enter in your graphing, in one version of what you would enter in your graphing calculator. To enter y1 of 1.2, you would push alpha, the green alpha button, trace. And when you push that, when you push alpha trace, you see a sub-menu pop up. You see a sub-menu that has y1, y2, y3, etc., etc., etc. At that point, you push enter, because when you push alpha trace, it comes default highlighted over y sub 1. So if you needed y sub 2, you would push the cursor down to highlight over y sub 2 and then alpha trace enter. So alpha trace enter, and what you see on your screen is y sub 1. Or if you have an older version of the TI-84, the newer version would also work with the keystrokes for the older, but the older will require that you do this the second way. Second way in I guess red. Or you push VARS, variables, then you access Y variables, which means you get the cursor highlighting over Y variables in the screen, which means push the right arrow button. Then you push number 1 for function, then you push number 1 again for y sub 1, and then you'll see in your screen appearing y sub 1. So this in practice, this goes very, very quickly. You would push in practice for this whole segment in green. You would push 0.2 times alpha trace enter, and in parentheses put 1.2. So in parentheses you would push 1.2. I sort of forgot to enter that. Or if you were doing it the other way, variables, y variables 1, 1, and in parentheses 1.2. Then plus alpha trace enter 1.4 plus alpha trace enter 1.6 plus alpha trace, etc. Or the corresponding keystrokes with the older calculator in the red indicated. Okay, and I realized it there in my red. It looks like y variables. It's x variables. Okay. Okay, play with it a little bit. If it seems a little intimidating watching this described, it's much easier. It's much easier done in practice, and you'll have plenty of practice on homework and stuff. Okay. In any case, you don't show all this stuff with the graphing calculator. You simply show the thing that's indicated with the first red arrow, and you show the approximation afterwards. You show exactly what your calculator has. All the decimals are important here. Show all the decimals and exactly the ones shown in your calculator. You're being graded on what your calculator is showing you. So don't round anything off unless you're indicated to round things off, and then you round things off. So I have to be real careful here. I got 0.645, 6 again, 349,206, 349,206. Okay, and that's our approximation. So you show the first thing in this sort of candy striped arrow, and you also show this second thing in this weird, ugly second candy striped arrow. Okay, that's all you got to show. Okay, so there's this first example of a integral approximation really is an example of what the rest are going to look like. We're going to develop now some more formulas. It's going to take us a little while. So this is why we're doing this in 2 segments. But we're going to look at better formulas actually. Okay, so the right and left hand endpoint approximations are not very accurate. There is a lot of error involved in using right and left hand approximations that can be improved upon with other methods. Okay, so that's what we're going to do for the remainder of this first part of this section. Let's see how we might improve our right and left hand approximations. Specifically, let's take a look at the right endpoint approximation. If here's our drawing again. So if A is our x sub 0, here's our x sub 1, x sub 2. In the first subinterval, imagine drawing a little rectangle corresponding to the right hand endpoint x1. And here's our first approximating rectangle. And this is a really good illustration of what I meant by it's a really inaccurate method compared to those coming up. Look at that rectangle. Look at how far above the actual curve it lies. Look at how much extra area that we have here. Look at how much of an overestimate this is to the actual area underneath the curve in that first subinterval. That's terrible. Let's draw another rectangle using the right-hand endpoint approximation. Look at that again. The error is awful. Terrible, terrible, terrible. Okay. So instead of using the right-hand endpoint approximation, or the left-hand approximation. The left-hand endpoint approximation would give us really just about the same terrible error as an underestimate. Instead of using the right-hand endpoint or a left-hand endpoint, let's use the midpoint of this first subinterval. Let's take in green, let's take a look at using the starred x values in the definition. Let's use that as the midpoint of the first subinterval. And from that point, let's go up to the curve and form a rectangle in green. Now look at that green rectangle. In the first half of the green rectangle, we have an overestimate of the actual error by the amount that I'm sort of putting in little dots here. It's an overestimate. It lies just too much area on that side. But in the second half of the green rectangle, the rectangle is giving us an underestimate. It doesn't go high enough to pick up the stuff that I'm shading off again. So we have an underestimate from half the rectangle and an overestimate from the other half. What's happening with the errors when we consider the entire interval, the first subinterval? The errors are sort of canceling each other out. In the left hand, the left half of the rectangle is giving us an overestimate by a certain amount, and we're not getting enough area in the second half of the first rectangle by a certain amount. We're kind of canceling out the error. And this is actually what's going on. This, by using the midpoint, we are effectively canceling out a whole bunch of the error that's produced in the right and left-hand approximations. This method that we'll call the midpoint rule is actually one that's used in industry because it is relative to the left and right-hand approximations. It's very accurate. So just so make sure you're following along, in the second subinterval, we'll choose the midpoint between x sub 1 and x sub 2. We'll go up to the curve at that point, and we'll form a rectangle. A very good approximation of the actual area underneath the curve in that second subinterval. Okay. So we should start giving some names to these midpoints that we're choosing. The midpoint in the first subinterval, we're going to call x sub 1, little bar above it. We're borrowing this notation from statistics. Okay, in statistics, this means mean or average. I don't think statisticians like you to use the word average for these, so they call them the mean. Okay. The average between x sub 0 and x sub 1 is the midpoint. The average between x sub 1 and x sub 2 is the midpoint, and so forth. And this is how the method goes. We would keep doing this until we got to the last subinterval between x sub n minus 1 and x sub n, and we would average those two endpoints of the last subinterval. We would go up to the curve at that point and form a rectangle. Oops, I guess I could fix my rectangle a little bit. A little better. Okay. Okay, so let's get a formula for this. This formula is very simple. Once you've gotten used to this notation, oops, x sub 2, this is x sub n bar. Once you get used to this notation, it's very, very simple. So we're going to call this a midpoint approximation. And in fact, we'll call it the midpoint rule. And the midpoint rule says that the integral from a to b of f of x with respect to x then is approximately the midpoint rule given by the midpoint rule with n subintervals, m sub n, and that's equal to the value of the function at x sub 1 bar times delta x. Here's the area of the first green rectangle plus the value of the function at the second midpoint times delta x plus all the way up to the end the value of the function at f of x sub n bar delta x. To make the formula a little easier on the eyes to memorize, it's delta x, just like the left and right endpoint approximations, times f of x1 bar plus f of x2 bar plus all the way up to f of xn bar. Okay, the delta x definition of delta x doesn't change. It's the length of each of the subintervals. Doesn't change through any of these methods. Okay, now there's a formula for x, the midpoints, x sub I bar. Notice that, let's just take a look at x sub 2 bar. That'll do it. X sub 2 bar. X sub 2 bar here. It's equal to the average of x sub 1 and x sub 2. It's x sub 1 plus x sub 2 over 2. So x sub 3 bar would be x sub what? 2 plus x sub 3 over 2, etc., etc., etc. So x sub I bar would be, if I was looking at the number I sub interval, just to get a typical one, x sub I minus 1 to x sub I typical interval, subinterval, x sub I bar, that little guy right in the middle, would be the left-hand endpoint, x sub I minus 1, plus the right-hand endpoint, x sub I divided by 2. Okay, formula looks real complicated, but it's not. It's just the average of the two endpoints. Okay, so let's take a look at the integral we're going to follow through the whole section. So example, use the midpoint rule with n equals 5, same n as is in the right-hand approximation, to estimate or approximate, same difference, integral from 1 to 2, 1 over x dx. Okay, so let's do that right now. Well, I think again that it would be a good idea for you to look at the x-axis, over the part of the x-axis over which we're integrating. We're integrating from 1 to 2. Now delta x is the same as it was before. Delta x is still 0.2. So we're looking at 1, then 1.2, 1.4, 1.6, 1.8, and 2. Okay, now I give you a formula for the midpoint, but I think that it's really easy to just use a little common sense to get the midpoints. So here's what I mean. What's the midpoint between 1 and 1.2? You could have 1 plus 1.2 divided by 2. You could average, or you can just notice that it's 1.1. Delta x, the distance between 1.0 and 1.2 is average the two divided by 2. Well, the delta x is 0.2. So the midpoint needs to be half of delta x away from 1. So half of 0.2 is 0.1, so 1.1. So the next midpoint then is what? X sub 2 bar between 1.2 and 1.4 is 1.3. So it's that simple for this problem. So x sub 3 bar is 1.5. X sub 4 bar is 1.7. And finally, x sub 5 bar is 1.9. So let's do this. Let's set up this midpoint approximation. So the integral from 1 to 2 of 1 over x with respect to x then is approximately equal to the midpoint rule with n equals 5, so m sub 5, which is delta x, and delta x is 0.2. It's delta x, look at the formula, it's delta x times f of the first midpoint plus f of the second midpoint plus f of the third midpoint, etc., times f of the first midpoint plus f of the second midpoint, f 1.5 plus f of 1.7 plus f of 1.9, and compute this. Use the technique that or the keystrokes that I showed you for the graphing calculator, and push enter, and all you show the line that I just drew or just wrote, and you show what the actual approximation is. My calculator gives me 0.6919, let's see, 0.78857. Okay. Okay. Notice what I'm not talking about here is error. I'm not talking about error at all, and that's on purpose. I mentioned earlier. I'll just say it again real quick that I'm only interested in the approximation methods in the first part of this section, in this first video that's going to cover this section, first of 2 videos. Okay. In the next video, we will look at exclusively error analysis. Okay. Okay. All right, so let's move forward. Let's take a look at our next approximation method. So you don't get too weary and wonder if we're going to cover like 100 methods. We're not. We're only going to look at after this method 1 more. So we have 2 more to look at. This next method is less accurate in general than the one we just talked about. The midpoint rule is very accurate. The midpoint rule is in some sense twice as accurate, and we'll discuss what we mean by twice as accurate in our next video. But this next method is the midpoint rule, the one we just covered, is twice as accurate as this next method. So we really need to question before we look at this method, why would we look at it? Why would we look at the midpoint rule, which is twice as accurate as this next one? Why would we even bother with another one? There's an important reason, and I'll bring that up when we're done with this method. Okay. Okay. So here's our next method. I've drawn 2 subintervals. We only really need to look at a couple of subintervals. Here's the first 2 subintervals involved in our integral approximation. Let's take a look at a rectangle that would be involved if we were to use a left endpoint approximation. If we were to use a left endpoint approximation, we'd go up to the curve in the first subinterval on the left, and we'd form a rectangle. Then we'd go to the second subinterval, go up to the curve from the left on the left-hand side, and come over. And we introduce a lot of error. These green rectangles give us an underestimate by a lot. Now, what I'd like to do with these little green rectangles is I'd like to construct, instead of rectangles, I'd like to use them to construct a simple figure that would wipe out some of that error. See this point that I'm identifying as the right endpoint in the first, the right upper right corner of the first rectangle. I want to attach that point up to the curve. I want to bring it up to the curve and attach it there. And I want to remove the upper part of that rectangle. So I'm erasing the upper part of the rectangle. And I'm going to connect the left-hand endpoint now then. The left-hand endpoint I'm going to connect. Give me a second here to fix my drawing. Oh, yeah. Okay. Here's my function. I'm going to connect left-hand endpoint with a line segment. Look at what I did with the error. I pushed the error out. I'm going to do the same thing with the second green rectangle. On the second green rectangle, notice the upper right corner of the rectangle. Push that up, push that point up toward the top of the curve. Then move, like I did in the previous one, move the top of the rectangle so that it becomes a line segment from the left-hand endpoint to the right up at the top of the curve. And look what I've done with the error. The error is now, they're still underestimates, but they're underestimates only off by a little sliver of error rather than the big, huge, almost triangular shaped errors that we had before. Those figures, those two figures are called trapezoids. These are called trapezoids. From geometry, trapezoids. A trapezoid is a four-sided figure where two of the sides are parallel, two opposite sides are parallel. Okay. So what we're going to do is we're going to use trapezoids to estimate the error. So we ought to come up with a name for this rule. Should we call it the banana rule or the Volkswagen rule? No. Let's call it the trapezoid rule. Okay, so in order to derive the trapezoid rule for you, which is very simple to derive, what we need is the formula for a trapezoid from geometry. So here, off to the side in red, here's the area for a trapezoid from geometry. Oops, I'm going to draw the two sides opposite or parallel. Here's a trapezoid from geometry. Trapezoid is a four-sided figure where one pair of the sides opposite each other are parallel. Trapezoid has two things called bases, base 1 and base 2. Trapezoid also has a height h. So the area of a trapezoid from geometry is half the height times the sum of the two bases. Okay. So our trapezoids, the ones we have pictured in green over here on the left, they're sort of on their side. So our trapezoids look like this. Let me draw it in. Let me draw this first one in green. Here's one of our trapezoids looks like this. Okay. Well, this point is x sub 0, this point is x sub 1. So the bases are now vertical. So the first base, B1 is f of x sub 0. Here's our second base, B2 is f of x sub 1. And this is our height horizontally here. Our height is delta x. So the area is h over 2, delta x over 2, times base 1 plus base 2, f of x sub 0 plus f of x sub 1. Okay, so let's get a formula for the trapezoid rule. You don't have to memorize the derivation that I'm giving. Okay, I'm not going to test you on the derivation, but I want you to see how easy it is to get this trapezoid rule. So the trapezoid rule. Trapezoid rule. Okay. Let's say T for trapezoid sub n sub intervals. Okay. So the integral from a to b of f of x with respect to x then is approximately equal to t sub n, which is let's take the area that I have over on the right in green of the first trapezoid. It's delta x over 2 times f of x sub 0 plus f of x 1. So let's figure out the area of the second trapezoid. It's going to be delta x over 2 again. Same height for all the trapezoids. The height is actually the width here. Times the sum of the two y values. The left y value is f of x sub 1. The right y value is f of x sub 2. If I drew in a third trapezoid, I'd have plus delta x over 3 times f of x sub 2 plus f of x sub 3. Okay, and this we would keep going, plus dot 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 until we got to the last subinterval. Oops, I wrote delta x over 3, I just realized here. I'm fixing that, sorry. In the last subinterval, we have delta x over 2 times the sum of the two y values in that last subinterval. And the one on the left in the last subinterval is the y value on the left is f of x sub n minus 1. The one on the right is the y value at b, x sub n. Looks like a complicated formula. It simplifies very, very nicely. Notice first that delta x over 2 factors out. Then we get f of x sub 0 plus f of x sub 1 plus f of x sub 1 plus f of x sub 2 plus f of x sub 2 plus f of x sub 3 all the way to the end. Now in the very end, we're going to get f of x sub n minus 1 plus f of x sub n. I didn't write it above, but the one just before it then will have plus f of x sub n minus 1 added to f of x sub n minus 2. Okay, still looks pretty complicated, but it simplifies in this last step. We have f of x1, f of x sub 0, of course. But we have f of x sub 1 plus another one. They're the same. We have two f of x sub 1s. We have two f of x sub 2s. So 2 times f of x sub 2. In fact, we have 2 times these, each of the next terms coming up, each pair, until the n minus first one, the next to the last one, 2 f of x sub n minus 1s, and we have an isolated f of x sub n. Okay, so this looks very simple actually. In the parentheses, we have f of x0, f of x1, f of x2, f of x3. The first and the last, f of x0 and f of xn, have a coefficient of 1. The rest of them have a multiple of 2, a coefficient of 2. And unlike the previous methods, left, right, and midpoint rules, we multiply not by delta x, but delta x over 2. It's a very simple formula to remember. Okay. Let's estimate our integral with this. Keep in mind, I still haven't answered the question, why would we consider something less accurate than the midpoint rule? Midpoint rule is in some sense twice as accurate as this method. So stay tuned. Okay, so let's use the trapezoid rule. So use the trapezoid rule with n equals 5 to estimate the integral from 1 to 2 of 1 over x dx. Okay, so let's do that. Delta x is still the same. Delta x does not change for us. Delta x is always b minus a over n, which is 1/5. Still 0.2. No change. No change here. From previous. Previously. Okay. So the integral then from 1 to 2 of 1 over x dx then is approximately t sub 5, which is, and there's our formula above, delta x over 2, delta x, 0.2, over 2 times. Now remember the x sub 0, x sub 1, x sub 2, etc. They were 1, 1.2, 1.4, 1.6, 1.8, and 2. F of x sub 0, 1, plus 2 f of x sub 1, 1.2, plus 2 f of x sub 2, 1.4, plus 2 f of 1.6, plus 2 f of 1.8 plus f of 2. Okay, look at how simple the formula is to actually use in practice. You keystroke this stuff into your calculator and you get t sub 5. T sub 5 is 0.6956 34 9206 9206. Okay, so I want to briefly answer the question, why would we need a less accurate method than the midpoint rule? Why would we need to look at that? Okay, a method that's half as accurate as the midpoint rule generally. Okay, the reason is the midpoint rule requires that we know the value of the function at midpoints. We may not have access to those. If you miss what I just said, for our function, x sub 0 is 1, x sub 1 is 1.2, x sub 2 is 1.4, 1.6, 1.8, and 2. We're assuming that we have a science application where we're able to access the y values at these points. Okay, so the left endpoint approximation, the right endpoint approximation, and the trapezoid rule will use these points, and they don't require that we would find, those methods don't require that we'll use a midpoint. The midpoint rule then requires that we somehow get y values at 1.1, 1.3, 1 at the midpoints, etc. And we may not have access to those. Okay, so the midpoint rule, while it's twice as accurate, requires that we get some additional data points or get y values at midpoints, okay, which we may not have access to. Okay, so that's one reason why we might consider a trapezoid rule. All right, so we've looked at 4 methods so far: left, right, midpoint, and trapezoid. Midpoint being the most accurate by a long shot, without defining formulas for accuracy and stuff for error. I want to look at, for our last method, an approximation method that is much more accurate than all 4 of these methods. So specifically, then much more accurate than even the midpoint rule. Okay, so let's do that. Here's a drawing of our first 2 subintervals again. And for this last method, we're gonna improve on the trapezoid rule. The idea is to improve on the trapezoid rule. Of course, the midpoint rule as well by a whole bunch, but we're gonna think about it as an improvement on the trapezoid rule. So what does the trapezoid rule say? The trapezoid rule says that we're estimating the integral, which we can interpret as the area for now under the curve, by using trapezoids, or by using line segments between the y values. Line segments. Well, line segments are very simple functions, and that's why the trapezoid rule is so simple. Suppose I wanted to take those trapezoids and bend the top of those trapezoids toward the curve, squeezing out even more error. What simple figure can you imagine, similar to a line, or similar in difficulty to line segments, but it's pretty simple? What simple curve can you think about that curves instead of is straight like lines? And the answer is parabolas. So instead of using line segments to estimate my area, what if I could bend those line segments in the form of parabolas to estimate the area? Now the problem is that we wouldn't be able to fit a parabola within the first subinterval, because a parabola requires 3 points to fit a parabola. That didn't come out very well. A line requires 2 points to find the equation of the line. A parabola requires 3 data points, 3 points to fit a parabola. So, in order to use parabolas to estimate the area underneath the curve, we're going to need 3 points at a time. So in order to, if you're not following along, in order to use parabolas to estimate the area within the first 2 subintervals, I'm going to need to use the 3 points that I'm indicating here to best fit a parabola. The best fitting parabola might look like this. Best fitting parabola, look at how it's squeezing the error out. Would come up, would bend again over, and if it would continue on down. One parabola would require 2 subintervals. Okay, so the next parabola used to estimate the area underneath the curve, or the integral, would require x sub 2, x sub 3, and x sub 4. So if the curve did this sort of thing, then the next best fitting parabola would require x sub 2, x sub 3, and x sub 4. And I don't know if I can draw this. Might look like this. It hits this point, and it kind of misses. Comes down, it hits this point, and maybe continues. My point is that in order for this next method to work, the method of, and it's not going to be called the parabola rule, we'll name it in a second. This next method, which uses parabolas, an improvement on the trapezoid rule, uses parabolas, requires an even number of subintervals. So n, for which is the number of subintervals for this method, must be even. There's no such restriction in the other 4 methods we looked at. We were looking at r sub 5, m sub 5, and t sub 5. And n was odd in those cases. N for this rule needs to be even. Now, for the trapezoid rule, I went back to geometry with you, and we looked at the formula for the area of a trapezoid. The formula for the best fitting parabola doesn't come from our geometry course. It's a little more complicated to derive. Your author does it in an example. You're not responsible for it. So if you're interested in seeing where this formula comes from, just check it out in one of the examples in our text. Your author does a pretty good job at it. Okay. So back to our problem. Let's look at our curve with our, I guess, first 4 subintervals showing there. I'm going to write in the y values at those points, f of x sub 0, f of x sub 1, and f of x sub 2. There would be the area underneath our first parabola. Well, the formula for the best fitting parabola with those three y values looks like this. And again, you don't have to derive this. The area is f of x sub 0 plus 4, there's a very strange number popping up, f of, times f of x sub 1 plus f of x sub 2. And it's not delta x over 2 in front, it's delta x over 3. Again, derivation of this is a little tedious, and if you want to see it, it's done in the text. You're not responsible for it. So that's the area underneath that first red approximating parabola. So using this sort of as the key, this as a pattern, what would be the area underneath that second approximating parabola, the one that's concave up or bending upward? It would be delta x over 3 times, we'll use this in what's in the first set of brackets as sort of a guide. It's the y value on the left, in which case it's f of x sub 2 for us now, plus 4 times the middle y value, plus the y value at the right endpoint. And this continues on and on and on until we get to the last two subintervals where we have delta x over 3 times, and we're going to involve the last three y values. The last y value is f of x sub n. The one just before that is f of x sub n minus 1, so 4 of those. And the one just before that is f of x sub n minus 2. Okay, it looks like a complicated formula. We're going to call this S sub n. If you've had this material before, you know what S stands for. I'll give that up in a minute or so. And I notice I can factor out a delta x over 3. So here's the simplified formula. F of x sub 0 is all by itself. And we have 4 f of x sub 1s. How many f of x sub 2s are there? There are 2 of them. There's one right there, and there's one right there. So we have plus 2 f of x2 plus 4 f of x3. Look at the pattern. 1, 4, 2, 4. How many f of x4s will there be? There'll be 2 of them. There's the pattern. The coefficients are 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, until we get to the end. 2 f of x sub n minus 2s, coming from those previous, 4 f of x sub n minus 1s, and 1 f of x sub n. It still looks complicated, but it's really not. It's a pattern. It's very easy to remember. The first and the last y values have a coefficient of 1, and in the middle we have 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, very alternating. Okay, and until the next to the last gives us 4, and then 1 is the last coefficient. This rule is not called the parabola rule, it's called Simpson's rule. Simpson's rule. Oops, Simpson's rule. Simpson's rule uses parabolas to estimate the area underneath the curve or the integral. The trapezoid rule uses line segments. Okay, and Simpson's rule, as you can tell just from the drawing, squeezes out tons of the error. It squeezes out even more error than the cancellation involved of the errors in the midpoint rule. Simpson's rule is many, many, many more times accurate than even the midpoint rule. Simpson's rule is. Okay, but again, we'll revisit Simpson's the error in the next video segment. Okay, so to finish up our video segment for today, or for now, I would like to use Simpson's rule to estimate the area, the integral. So use Simpson's rule, that parabola rule, Simpson's rule, the one we just looked at, to estimate the integral from 1 to 2 of 1 over x dx. And we've been using n equals 5. Why can't I not do that? Because Simpson's rule requires n to be even. Now, I always ask this in a live lecture, and most of the time I get the wrong answer, or not the best answer. So think about this. I cannot use n equals 5 because n equals 5 is an odd number. What should I let n equal? Most students will say 6. Use n equals 6. Well, I say use n equals 4. And then the typical response from students is, well, don't you want the most accuracy possible? And my response is, yes. But Simpson's rule is so accurate that I want to use n smaller. See, the larger n is, the more accurate our methods are, but I want to come down for Simpson's rule. Simpson's rule is so accurate, and I could use a smaller number of computations and probably still get something more accurate than the midpoint rule. We're going to talk much more about error coming up in the next segment. I keep saying that. Stay tuned for that. But I want to use n equals 4. I'll justify that even more in the next video segment. Okay. So with n equals 4. So with n equals 4 now, we have a change in our quantity. Our quantities. Delta x is no longer b minus a, 2 minus 1 over 5. It's 2 minus 1 over 4. So our delta x is 1/4 over 0.25. So along the x-axis, x equals 1. Delta x is 0.25, so x sub 1 is 1 plus delta x, or 1.25. X sub 2 is 0.25 away from that, so 1.5. 1.75 for x sub 3, and 2 for x sub 4. Okay, so s sub, actually let me go back. So the integral from 1 to 2 of 1 over x with respect to x then is approximately equal to s sub 4. Now Simpson's rule has as a coefficient of the brackets delta x over 3. Always over 3. So delta x is 0.25 over 3 times. And remember, the coefficients alternate between 4 and 2 after the first starts out, the first coefficient is 1, 4, 2, 4, 2, 4, 2 after that. So f of 1 plus, here's our first 4 f of 1.25 plus 2 f of 1.5 plus 4 f of 1.75 plus the value at 2, f of 2. Alternating 1, 4, 2, 4, 1. Okay, we would key this into our graphing calculator, and our last approximation then would be approximately 0.69325 9681. Okay, now that's our last method for this video segment, and next time we will analyze error. So I'm looking forward to talking with you about error next time. Until then.